right, good morning. It's my great pleasure to bring to you our keynote speaker, to introduce Sir Roger Penrose. Roger is well known in many areas of science, philosophy, and mathematics. He's very well known in physics for his work on black holes, general relativity, cosmology, including his new theory of eons preceding the Big Bang. Mathematics, geometry, tiling the plane, fivefold symmetry. He received the Wolf Prize with Stephen Hawking for contributions to understanding of the universe. He was knighted in the early 1990s for his contributions to science and mathematics. He is currently the Emeritus Rousball Professor, the Mathematical Institute at Oxford, and also at Wadham College. In 1989, he wrote a book in which he turned to the study of consciousness, a very controversial book called The Emperor's New Mind, in which he questioned the assumption that consciousness is equivalent to computation, that there's some other factor involved, namely something to do with quantum physics connected to the fine scale structure of the universe, a connection that attempted to not only explain consciousness, but to resolve to some extent discrepancies between general relativity and quantum mechanics. And subsequent to that, he teamed with an unknown anesthesiologist in Tucson, Arizona, to develop the OR theory. But he's not going to talk about microtubules today. He's going to talk about consciousness and the laws of physics. It's a great pleasure to introduce Roger Penrose.
Well, thank you very much, Stuart. It's a great pleasure for me to be back here at one of these conferences. I guess 25 years ago was 20 years ago. Yes, I'm losing count, you know. You'll see I'm probably losing it a bit, and you'll see that in my talk, I expect. Anyway, the title, Consciousness and the Laws of Physics. I shall start by talking about consciousness, but only a very small part of consciousness. And you might ask why I'm not talking about all the other things to do with consciousness. Well, I want to explain, first of all, that I take the view that consciousness does something by virtue of being consciousness. It does things that non-consciousness can't do. Now, I know we were hearing yesterday about various ideas about consciousness. It always seemed to be the view that somehow you couldn't tell whether consciousness was in action or not. But it seems to me there are some areas where you can make a good case that consciousness really is doing something. Let me mention a few things where it's not very easy to make a good case. Conscious mentality has many manifestations, and I list a few things here. Pain, the sensation of blue, love, appreciation of beauty, disgust, joy, hope, free will, etc. And I'm not going to have much to say about most of these things. The one thing that I shall concentrate on is understanding. So understanding, seems to me, is something that is a manifestation of consciousness. Certainly in normal use of the word, I mean, you often say whether your computer understood something or didn't, but that's not really understanding. What do we mean? When we use the word understanding, we really imply that there is some awareness going on. So the idea, in normal usage, you wouldn't say that an entity understands something if it's not even aware of it. So I regard understanding, the presence of understanding, as an indication of some consciousness being present. And I shall be concerned particularly with mathematical understanding, not because there's anything special about mathematics here, except that it's where you can make rigorous arguments. So I want to say that you can make rigorous arguments about the role of understanding in mathematics, and that's the only reason I'm talking about mathematics. Understanding plays big roles in many other areas, obviously, but when it comes to mathematics, it's very interesting that one can make statements which seem to demonstrate that there's something other than computing going on when you understand something mathematically. Okay, so that's really the reason I'm talking about mathematics here. Other reason is that that's the sort of thing I know more about, but that's not the point here. Let me start with something. Some of these things I'm going to show you I've done many times before, so if you've seen them before, don't worry. I'm using the old slides often. Here's one. This is a chess position, which I have used many times before. I think it's a very nice chess position. It is one of a set of problems. Half the problems, chess problems, it was a kind of Turing test. Half the problems were easy for humans and hard for computers. The other half were the other way around. Easy for computers and hard for humans. And it became extremely easy to tell which were the computers and which were the humans. I want to give you an example which is easy for humans. Well, you have to know the rules of chess, of course, and something about the game, but not too much. This is a position where white has to play and draw. Well, white, of course, is brown here. And the idea is, well, what do you do? Well, if you know anything about the game of chess, what you don't do is take the rook. You see, black has a tremendous advantage. He's got 2 extra rooks, and if you take the rook, there will still be another extra rook here, and so you pretty well lost the game. So that's not a good thing to do, but what a good thing to do is just stop short of taking the rook, place the bishop here, and then you have a barrier of pawns across which the black pieces cannot get. So all you have to do is wander your king round the back here, and there's no way you can lose the game. So anybody who plays much chess will realize that's the thing to do. You just block the black pieces off, and there you are. But this is just an example of something which computers find difficult because they haven't got the idea. I mean, you could build these things, post hoc. You could make your computer look for chains of pawns or something, but that's not the point. The point is that that is not the way chess computers are programmed. They're programmed to calculate all sorts of possible move after move after move after move after move like that, and see whether by some counting the position has improved or not when you have some chain of moves. Well, in this particular case, if you take the rook, it takes a long time for the black to let the rook out of the corner and so on and move it out through the hole and start causing damage to the white pieces. But it's just an example. I'm not making a particular thing about this particular position. It's just an example to show where a little bit of understanding, in this case, can get you a long way where brute force computation is very difficult to achieve the same result. In the other sets of positions, understanding doesn't help you much. It's just brute force. So it's a good way of distinguishing what you can do by brute force or what you can do by understanding. Now, one trouble with chess, as a demonstration here, is that it is a finite game. And so you could clearly imagine that, I don't think it's happened yet, but in the future there will be computers so powerful that they simply can work the whole thing right out to every possible move, right from beginning to end, and chess will be completely solved. Then, well, a little bit not very nice situation for chess players, I suppose. But the point I want to make is chess is a finite game. I think if I want to cover things over, I should probably put a whole lot of these on. Chess is a finite game, and if you want to make a clearer demonstration of a difference between understanding and brute force computation, it's better to think about the infinite. Someday, maybe chess will be completely solved, but in mathematics, one is often concerned with the infinite. And the question is, how might computers be able to deal with the infinite? With human understanding, we can often deal with infinite issues in mathematics. People sometimes think, well, infinite is something you can never understand, but that's certainly not true. You can deal with the infinite in many ways in mathematics, and it's very powerful when we do so. The question is, in this case at least, you can't expect to run through all the possibilities because there are an infinite number of them. Now, I want to give you some very simple examples of how, or one very simple example, of how human understanding can deal with the infinite. And these are very simple things which I'm sure people are familiar with. I want to talk about mathematical induction. Well, mathematical induction is a method of proving some proposition is true which depends upon n. So it's proposition number 0, and n is a natural number, and my natural numbers start with 0. That's just not important. But let's say P of 0 is one statement, P of 1 is another statement, P of 2 is another, P of 3 is another. So it's an infinite number of statements, but they're kind of systematized in some way. Now, how do you use mathematical induction to prove P of n for all n? That's an infinite number of statements. Well, what you do, first of all, establish that P of 0 is true, and then you establish that if it's true for P, if P of n is true, then P of n plus 1 is true. And that's a finite thing. You do this one and you do this one. There's two things you have to do, and you've now proved P of n for all n. This is also technically, if you have the rules of logic built into some computational system, this is what's called first-order piano arithmetic, and it is a computational system. This is something that you could apply in a computational way, and you have to use your understanding to know this works, but when you've used that, you could put this on a computer. But I want to make, well, first of all, let me give you an example. I'm sure you've seen these things, but let me give you an example. Here's an example. If you want to prove that for any n, the sum of integers from 0 up to n is equal to a half n times n plus 1. Well, you establish it's true for 0, because you've got 0 on that side and 0 on this side, and then you say, if we accept it's true for n, then do we see that it's true for n plus 1, and it's just a calculation, which you can follow down there if you like. The details are not important here. But what I do want to say here is rules like this, which you could put on a computer, do not exhaust what one can do with one's understanding. And this is because of the famous Gödel theorem, which I'm going to give in Turing's version, which is to say, given any computationally checkable set of proof procedures, the point is that these procedures could be checked by a computer to see if they're correct or not. If the computer says, yep, okay, then you've got a proof. That's the idea. Now, what Gödel says is for any such system of rules R, you can construct a well-defined mathematical statement G of R. This is a statement dependent upon these rules, which can be seen to be true on the basis of the same belief system that provides our trust in R itself. Now, this is a subtle point, but it's a crucial one for the argument. People often think, well, how do you know R is consistent or something like that? But the whole point is, you have to believe in R or you wouldn't use it. What's the point of having a proof that you don't believe in? I mean, the idea of a proof is that you believe it gives true results. Now, if you weren't convinced that R was consistent for some reason or other, whatever, if you weren't convinced about that, then you wouldn't be convinced of any conclusions. Because if it's inconsistent, then you can prove anything with it, anything within the system you're talking about. So the very fact that you're using R as methods of proof that you trust reliably enables you, that trust, if you like, enables you to transcend it. So the idea is that you use your understanding to transcend this rule following. Well, I could give you this argument in detail. It's not that hard. I could give it to you in detail, and you could follow right through from beginning to end, but it's not really worth giving you that here. The point is that the statement G of R, constructed from the rules R, can be seen to be true if you trust R as a reliable system of proof procedures. So that's the key point. Somehow, whatever understanding we use to believe that R is a reliable set of proof procedures, that same set of beliefs, if you like, that same understanding that R works, enables you to transcend R itself and get something else. So this is the key thing about the Gödel statement. When I first heard about Gödel theorem, this is when I was an undergraduate, and I thought it said, shows there are unprovable things in mathematics. I didn't like that idea at all, and I was very happy when I went to Cambridge and studying something completely different, but I went to the course on logic and Turing machines, and I realized in that course, the lecturer, a man named Steen, made it completely clear that something, just more or less what I just said here. So there's nothing controversial in what I'm saying here. this is completely accepted, that the procedures that go from R to G of R also are things, okay, it takes a little work to make sure you get it straight, that you trust it, that yes, there's no, I mean, there's subtleties involved, but there's nothing that's questionable about the reasoning. So, okay. Now, there are various problems people have with this, and for some reason, I don't know why, I get attacked very brutally on this particular issue, whereas it's completely clear logically, and sometimes you see I might, in Shadows of the Mind, there are one or two places where I made a few careless slips about certain issues, and people pounced on that and say, oh, no, it's all wrong. Well, in the second printing, it's corrected, so as far as I know, it's essentially correct. And the logicians that sometimes were a little bit annoyed with me because I was a bit sloppy probably in the way I present my arguments, not formally in all that way. You usually find that they have exactly the same views I do about these things. Anyway, I just want to emphasize, if you've seen sort of arguments about this kind of thing, there isn't any, it's certainly correct, this. Okay. Now, see, you can make certain complaints about this. See, what this seems to be saying is that with our understanding, any set of rules, we can transcend those rules. And where does that understanding come from? Well, there are all sorts of complaints you could make about it, and I want to address those in a minute. But one of these, let me address first, is that G of R is going to be very complicated, usually. Given a set of rules R, G of R may be really complicated. Now, actually, that doesn't matter for the discussion, because you can understand the arguments and you can understand, even though it's complicated, you can see that it's true. So it doesn't matter that it's complicated. But let me give you an example. I think there's some mathematicians who say, well, we're not going to worry about these things because they're of no interest. But let me give you an example of a G of R. This is one which is actually a Gödel statement to the system which I referred to previously, this thing called first-order piano arithmetic. So it's basically the induction principle. So if you have this way of establishing infinite things, how far does that get you? Well, it doesn't get you everywhere, because it doesn't get you to the thing I want to describe in a minute. And here I do want to cover some things up just to begin with. I hope that doesn't irritate you. I know it does some people. I don't know why, because on PowerPoint, of course, you can do things completely like that without anybody ever complaining. Okay. This is Goodstein's theorem. Prove it's not working, is it? Well, that's genuine complaint, yes. Why is it not working? Did I inadvertently press a button? Very probably. Sorry? It's fine? It's not fine.
Take off the paper, please.
Oh. Yes, now that is one of these little problems I've seen before. Good old overhead projectors, they don't do that. Yes. I hope you can see it at the bottom here. I can show you that. Well, I'll show you down there. Yeah. It's best all right, never mind. Goodstein's theorem proved in 1944. Take any natural number, that's non-negative whole number, and I'm just giving you an example to illustrate it. I'm going to try the number 1077. Could be any other natural number, don't worry. Then you write that number in binary. Well, that's familiar to people, 1001 and all that sort of stuff. The first one stands for 1024, the next one for 32, and so on. So you're expressing your number as a sum of distinct powers of 2. And here they are, 2 to the 10th plus 2 to the 5th plus 2 to the 4th plus 2 squared plus 1. Now, this procedure of expressing numbers in sums of distinct powers of 2 can also be applied to the indices up here. So 10, that's 2 cubed plus 2, 5 is 2 squared plus 1, and 4 is 2 squared. Okay? Now you notice there's a 3 up there. I haven't done that to it. So I'm going to replace 3 by 2 plus 1, and now I've finished doing that. Okay. Now I might have to go up chains which go up higher than this, but this is as good an illustration as any. Now I'm going to do two things to this number. First thing is A, which is replace all the 2's by 3's. So A, each term will be replacing 2's by 3's and then 3's by 4's and so on like that. So that's A. 3 to the 3 to the 3 plus 1, etc., etc., etc. This number just with 3's in place of 2's. B, what's that? Subtract 1. So okay, there's a nice handy 1 hanging out there. Let's get rid of that. Then that's the number, the green one there. What is A? Well, I replace all the 3's by 4's. There they are. And subtract 1. I hope you can see it when it's down at the bottom there, but of course it disappears if I cover it up. I don't know what to do it. Perhaps if I just cover a little bit up, it won't disappear. Okay, there we are. All the four, well, you see there are these coefficients, which are 3's. It's like when you use the ordinary decimal system and you have 99999, you see. Well, any number up to less than 10 for the decimal system would be a sort of, that doesn't count. You write them down. So 4 is now the base, and I have 3's as coefficients. Now I replace all the 4's by 5's. There they are, all the 4's by 5's. And the coefficients just stay the same, but that's all. So the 4's go to 5, subtract 1 again. Okay, and I just keep on going. What happens? Well, I start with 10 to the 177. I start with 1077. The next number, the green ones, are about 10 to the power 40. The purple ones are about 10 to the power 600. The brown ones are about 10 to the power 10,000. And they go up and up and up and up and up and up and up. And finally you get to 0. That's Goodstein's theorem. Whatever number you start with, you provide these two procedures. The subtracting one wins. It's a good hare and the tortoise example, where the tortoise wins every time. So even though these numbers get huge, absolutely huge, and this is, you take a number a bit bigger than that, and they're just vast. They would completely make your computer overflow with any decent-sized number here. This one probably would anyway. The other thing I want to say about this, not the surprising fact that it goes to 0 every time, but you can't prove it by mathematical induction. This is a theorem due to Paris and Kirby, and it's an example of a Gödel theorem. And it's a nice example because I can explain it to people who, all you have to know about how to deal with exponents. You know, what does it mean, 2 to the 10 and 2 to the 2 to the 2 to the 10 and things like that. But once you've got the hang of that, you can understand the theorem. Whether you believe it is another question. And the proof of it, I should say, you can't do it by mathematical induction. Yet, I'm not going to do it here, but you can sort of see why it's true. See, roughly speaking, these numbers, they spill off the exponents here and give you a long change like this. And you chip away, and then another one of these towers falls down, and you chip away, and then another tower falls down. And it keeps on doing that. And the numbers get... It's worth, just to get the feeling of this, try it first with 3. It comes down pretty quickly. Then try it with 4. And I wouldn't recommend putting it on your laptop or your mainframe, but you can see if you can convince yourself that with 4 it comes all the way down again, which it will do eventually. And for any number, it comes down again. But you cannot prove that using mathematical induction. Yet, it's something, with a bit of work, you can see it's true. With using the right mathematical reasoning, you can see it's true quite directly. That reasoning is what's called transfinite induction. I'm not going to bother you with what that is, but it is a procedure which is perfectly good, and you can see, once you get hang of these rules, that you can prove it perfectly well. Now, this seems to be saying that we can somehow use our understanding to show things in mathematics where you don't have the rules to show it. You see, I'm only talking about ordinary integers, ordinary positive numbers, positive integers, non-negative integers, and so the statements aren't all that difficult to state. The proofs, though, can be really quite subtle. Now, I'm going to give you the sort of arguments that are frequently made against the claim that one is evidently, therefore, using in one's understanding something beyond computation. The commonly raised arguments against this, I call it the Gödelian case, that we are non-computational beings. First of all, the errors argument. In fact, curiously enough, this was Turing's let out, because he started off, he knew all about these things. He started off, in fact, wrote some papers before his more famous one about computable numbers and so on, trying to explore how you might go beyond the ordinary idea of what we call a Turing machine. And so he was interested in that kind of issue about how we understand things and how we seem to be doing things non-computable. But I think after his work in the war and realizing how powerful computers were, he changed his mind and took this following, I think, rather implausible view that was I call the errors argument, that human mathematicians make errors so that rigorous Gödel-type arguments do not apply. And that was his let-out. In fact, if you want an actual statement due to Turing, this is a lecture to the London Mathematical Society in 1947, and he says, if a machine is expected to be infallible, it cannot also be intelligent. So he thinks it's got to be fallible to be intelligent. It's an interesting idea. There are several theorems which say almost exactly that. And the theorem that I just gave you earlier on is basically what he's talking about. But these theorems say nothing about how much intelligence may be displayed if a machine makes no pretense at infallibility. Well, I just find this pretty implausible. I'm rather surprised to use that argument, but I suppose he got converted to the ideas that computers, well, indeed, he was very much involved in this and showing you how universal machines could exist, and we now know how useful they are with our laptops and our mainframes and goodness knows what. But I do think it's an implausible let-out because, first of all, human mathematical errors can be corrected. If you make a mistake, well, quite likely somebody else comes along. So I was looking at your proof, and I think there's a mistake on line 57. And you go back and say, oh my God, you're right. Now, you can see it's a mistake. It's not inbuilt that these mistakes are somehow things that that you have to have in order to be able to be intelligent or something. It doesn't seem quite to make sense to me. I may say I have a tremendous respect for Turing. It's just that this particular thing, I'm not quite sure why he took that line. The other point is, well, I say they're corrected by others, or quite often by the same human. You go back and look at his proof. I hope this is all right. And, oh my God, look, I made a mistake there. I mean, that's not the reason that to be intelligent, you don't have to make mistakes, although even intelligent people make lots of mistakes. It's easy to make computers make mistakes too. You see, that also is the other end of the story. If you want to make your computer intelligent, you just make it make mistakes. Well, I don't think that's I don't think that's too convincing. Okay, what about the other arguments? Well, the extreme complication argument, you see, I want to use a different way of addressing. I did in Shadows of the Mind try to attack these things in a logical way, and I made it incredibly complicated. I think that one can make a different argument, which is much simpler, and I'll give you that in a minute. The extreme complication argument is that the algorithms governing human mathematical understanding are so vastly complicated that their Gödel statements are completely beyond reach. Okay, that's one possibility. Now, this is actually quite an important one. I call it the Gödel let-out. You see, Gödel knew all these things, of course, but he was not totally convinced that that was a rigorous argument that we were not computers. He didn't believe we were computers, and he had some other slightly strange ideas about it all, but I think the thing that he missed, basically, was that he thought physics was necessarily computational, which is perhaps a subtle point. But this is a perfectly valid argument, that ignorance of the algorithm argument, you see, if you don't know the algorithm, you can't construct its Gödel statement. So there might be some algorithm in the backs of our heads which is making us do good mathematics, but we don't know what it is. And so it's hard to construct the Gödel statement. Now, I had various ways of getting around that in Shadows of the Mind, but I'll give you a different argument in a minute. See, we do not know the algorithmic processes understanding our mathematical understanding, So we cannot construct its Gödel statement. So that's the Gödel let out, if you like. So although Gödel didn't think we were computers, Turing apparently did in his later life, although he didn't earlier on. And let me try and address both these arguments in a different way. The different way is the following. I want to give you a picture from my book, Shadows of the Mind. And here we have some ancient human beings, and these are people who are using their understanding to grow crops here, or domesticate animals, or build shelters, or whatever it happens to be. And here's one who's had a brilliant idea about how to catch mammoths, you see. Okay, they're using their understanding in various ways. And here, in the middle, we have a mathematician who is fiddling away trying to do some mathematics and completely unaware of the saber-toothed tiger that is about to pounce on him. The point I'm trying to make here, this is an argument from natural selection, that an ability to do sophisticated mathematics was not a selective advantage. It's probably not one now. Many of the mathematicians I know don't make huge salaries, for example. So it's not obviously a selective advantage. In fact, to do things like Goodstein's theorem certainly wouldn't be. A general ability to understand was. So what I'm trying to say is that a general ability to understand was the quality that was selected for, and that was what these other people were using, and that's probably what the mathematician was using too, but in its specific manifestation in mathematics was in itself of no particular selective advantage. That's the point I'm trying to make. And you might think of the Goodstein theorem. Now, what on earth would an understanding of the Goodstein theorem be selectively? Well, I mean, you're talking about ridiculously large numbers that certainly those ancient people would have never come across whatsoever, probably count up to about 10, I have no idea. Might be good enough. But to think about numbers like this, and to think about the reasoning that goes into this, and to have an algorithm inbuilt into your head which can deal with this, seems to me completely unreasonable from the perspective of natural selection. Natural selection didn't produce very sophisticated algorithms that can deal with things like this. It was producing some quality that is an understanding, a general quality of understanding, and that quality of understanding is something which I think is demonstrated to be non-computational. Okay. Now, this is an issue, I've just described this with regard to mathematical understanding. That's where the reasonably rigorous arguments come in, and that this is something non-computational, something that we don't have inbuilt our heads, some algorithm of such sophisticated nature that we can't grope to its Gödel statement. It seems to me that's not reasonable. We don't have algorithms like that built into our heads. We do have an ability to understand, but this general ability to understand contains the ability to appreciate the Gödel theorem and to build up more and more sophisticated systems and so on, so that you can use it in mathematics. But nevertheless, it's the general quality of understanding which is what was selected for. And that's what I'm arguing about. What about human consciousness? Well, you see, I did at the beginning mention qualities of consciousness, which, okay, they seem to be things which there's no reason why they should be computational if understanding isn't. And it seems to me that to draw the line where things become computational between human understanding and human consciousness doesn't seem to be reasonable. In fact, most things in consciousness are more obviously not computational. I mean, somehow the feeling of happiness or the perception of the color red or whatever it happens to be, or an appreciation of music or whatever it happens to be, all those things don't seem to be very computational. You might think mathematics is the most likely thing to be computational, and here you see it's not. So I wouldn't draw the line here either. What about between humans and animals? Personally, I wouldn't. Seems to me that, well, that saber-toothed tiger was probably conscious also, and it had a lot of understanding. It realized that mathematician was easy meat, you see. So there was probably understanding and consciousness quite deep down in the chain, if we can call it a chain, of animal existence. So I certainly believe that. How far down, I wouldn't like to say. What about life? I don't know. What about plants, for example? I don't know. Whether there's any kind of consciousness involved in plants, I'm not going to make any statement. But personally, I would consider, whatever this thing is, the key issue is consciousness. And that is the thing which, as revealed in our understanding, is something outside computation. So that's my view here. And I think the case is really pretty strong that what consciousness actively does, and it actively does it in our understanding, it's something which comes out. You see, it's not just an internal thing which sits inside and doesn't manifest itself outside. It's something which has an external effect. So I don't regard consciousness as something which could be there or not and you'll never know. That it has an objective effect outside in the world. And an instance of it is in the mathematical things, but I think it's true also right down the line here. So, the question therefore is, consciousness, what on earth is that? And where does it come from, and how could it conceivably be something non-computational? Well, you could take all sorts of views about this. I mean, maybe consciousness is something comes in from nowhere or from somewhere, and it's nothing to do with the physical world. It's just sort of imposed upon the physical world. It comes in and allows you to do things. I don't take that view. I take the view that whatever it is that our brain is doing, including the manifestation of consciousness and whatever consciousness actively does, is consistent with the laws of physics. However, there's a little bit of a catch here. What kind of physics might be beyond computation? And then you go and look at physics. You study the different things in physics. Well, you take Newtonian particle physics, particles hitting each other and forces and all that kind of stuff. Well, you see, there's first a little point that you have to worry about, because the very notion of computation, as defined by Turing and others, is something which depends on discreteness. You're talking about numbers, whole numbers, whereas physical laws depend on continuous parameters. And that's true also with classical particle physics, because you have to know what the velocity of a particle is and its location, and all these things are defined by continuous parameters. I'm taking the view, as Turing did, that that's not relevant. It might be, that's a guess if you like, that you can certainly in many areas of physics, astrophysics for example, very, very powerful simulations are made on computers of continuous systems. They can be stars running around each other, or they can be gas, plasma, all sorts of things that you can calculate, behavior of black holes or something. You can calculate these things to very, very great precision. And that precision is to a certain number of decimal places, if you like, but it's good enough. And although you're dealing with continuous parameters, the calculations are done with discrete mathematics. Now, I say that is a bit of a lacuna in the argument. You might say, well, there's a big difference there somewhere, really. I'm trying to say, probably not. It might be. I'm not convinced about it. But I'm saying that that's not the place to look. That there's something else which we have to think about here. Well, what about classical field physics? Now, that would be, for example, the initial archetypal example was the gravitational field was done this way, and then we have Maxwell's equations for electricity and magnetism and light. So these beautiful equations due to Maxwell are an example of field equations. Now again, you see, you're dealing with continuous parameters, not discrete things. But the way we do that when we compute is we approximate with discrete numbers and get away with it to as good a degree of approximation as you like. What about quantum physics? Well, I'll say a bit about quantum mechanics. That will be something definitely part of my talk. But I'm going to say we're going to need to go beyond quantum physics. So let me address that issue, first by telling you, I'm going to assume that you're not all experts on quantum mechanics. So I'm going to give you a rapid introduction to what we need. Now, I hope don't worry too much about the details. But I do want to emphasize a few points here. And this is rather made clear by these two idealized experiments. Here we have a laser which emits individual particles. Let's say a single photon comes out here. And we have detectors here and here. And here we have, well, sometimes people would call it a half-silvered mirror, or more technically, a beam splitter. What it does is that half the light that impinges upon it gets transmitted, and the other half gets reflected. Now that would be all right, you see, if light is just some continuous thing, and then, okay, half gets through and half is reflected. But if it's a single photon, a photon is a single unit of light. And if we have detectors here and here, what you find is that either this detector, I'm assuming these are idealized, you see, either this detector receives the photon, or this one does, and it's exclusive. Never it's both, never it's neither. It's either one or the other. It behaves just like a particle which comes along and decides here whether to be reflected or transmitted, if you like. However, that doesn't work for all experiments, and here we have another one. This is called a Mark-Zender interferometer. Here we have, again, a beam splitter here, two ordinary mirrors, and another beam splitter here, and let's suppose all these lengths are equal. Detectors here and here. Amazingly, you find it's only this one that detects the photon. So the photon never comes this way. Now you might say, well, the photon's got to be going this way or this way, so it goes this way or this way. And if it comes here, well, then it goes this way or this way. If it comes here, it goes this way or this way. Why doesn't it go here half the time and here half the time? It doesn't. But somehow the roots out this way mysteriously cancel themselves out, and it always goes this way. Now this is sort of particle-like behavior. The particle behaves just like a single entity. This is like a wave where you have to think of these little ripples, and the ripples cancel each other out, going this way, and they go this way. That'll work for a while, but it's a temporary answer. You have to go a little further to make sense of all these things, and let me give you the general thing you do. What is the photon doing between here and here? Well, it's somehow doing both things at once, and that's the sort of thing you get used to in quantum mechanics. There are two alternatives, and this is a general statement now. A statement can be a superposition of two alternatives. Alternative A is going this way, alternative B is going this way, and somehow it does both at once. Now, if it was an ordinary classical particle, that would be ridiculous. It's got to do one or the other, but that gives you the wrong answer. You never get it not to come here. Another rather mysterious thing is that these coefficients here, you say it's not just one plus the other, it's one times some funny number here, plus one times a funny number here. And you might think these were probabilities of doing one or the other, but that doesn't work either. These things have to be complex numbers, square root of -1 coming in, you plot them in a plane, and so on and so forth. Okay, that's what you do. Very strange, but that is what works, and it works, and it works. Now, linear. Quantum mechanics is linear. I'll say a bit more about that in a minute. That means that these numbers here stay fixed, and the evolution over here and the evolution over here simply go on their own merry ways independently. So that the sum of the evolutions is the evolution of the sum. I'll come back to that one in a minute. I'm going to call that U. That says unitary evolution. Unitary evolution is another way of saying the Schrödinger's equation. Schrödinger's equation tells you how the state of a system evolves in time. Then there's a completely different thing you do, and that's the measurement process. You make a measurement, suppose I made a measurement here, and that's what's going on with these detectors. Then suddenly you take the superposition, you look at these coefficients here, you take their squared moduli, that means the square of the distance from the origin in this diagram here, and those give you the relative probabilities of two things. So one thing or the other thing happens when you make a measurement. I don't want to go into that in any detail. I'm calling that R, that is the reduction of the state. Somehow the state collapses to one alternative or another, and that comes about when you make a measurement. Now, see, when you make a measurement, you've got some device, like these detectors here. Now, you might say, well, surely, If particles are quantum mechanical, and 2 particles and a zillion particles behave quantum mechanically, the detectors should behave quantum mechanically too. So if you have this superposition between A and B here, okay, this detector will be in a superposition of receiving A and not receiving A. But that's not what you do. Detectors don't do that. They're classical things. And that was how the Copenhagen view of Niels Bohr and Heisenberg, they said, well, look, we don't really understand what's going on, but let's make a few rules. And the rule is that detectors you treat as classical things. It's cheating, clearly, because the detector is made up of particles and so on, and they're supposed to be quantum things. So there is this thing that I'm referring to as the measurement paradox. It's usually called the measurement problem, but it's much worse than that, really. It's a paradox, because you can't use the rule U, the unitary evolution or the Schrödinger's equation, to tell you how the detectors behave. That doesn't give you the right answer. The right answer is the probability thing, and that's what you always see in quantum mechanics. Something very strange going on. Okay, well, let me say a bit more now about the linearity. I make this a little bit stronger here. Suppose we've got a laser here emitting a single photon, and it goes along and hits a green thing. Let's say it's a high energy photon, really high energy, so it hits this green thing, whoomph, all sorts of stuff come out of it, okay? You put in a mirror, it hits the brown thing, and whack, a whole lot of other things come out of it. Now you make that a beam splitter. Whoomph and whack happen together. It's a superposition. Linearity says that since these 2 photon states are in superposition, and because linearity just preserves each evolution independently, whoomph and whack, whichever it was, happen together. Okay, well, that's what you do in quantum mechanics. Now, I'm going to show you Schrödinger's cat. Everybody's heard of Schrödinger's cat. I want to make clear that Schrödinger, I think, at least in my belief, Schrödinger didn't believe that cats could be dead and alive at the same time. However, he showed that according to his equation, okay, here we have a photon going along, hitting the detector, bang, poor old cat. But let's do the other one, put in a mirror, and reflect it away from the mirror, happy cat, okay? But of course you know what I'm going to do. I'm going to make this a beam splitter, and as we have seen, the photon goes superposition of this way and this way, therefore the cat is in a superposition of being dead and alive, and that's what is referred to as a Schrödinger cat. He did it with poison. I'm doing it with a gun here. Not an important fact. You don't have to kill the cat, actually. It makes just as good an argument without doing that. But just this was his version, I think, for a dramatic effect. There is a little problem that the cat has its own consciousness, and you might worry about what that has to do with the situation. I'm going to ignore that here. However, you do have to worry about, see, people, I show this to physicists, and they say, oh, well, that's all very well, but you've forgotten to put the environment in. The environment makes all the difference. Okay, put the environment in. There it is. And then I go back, and I put the other one, and I'll put its environment in too. There we are. If you remembered where all those dots were last time, they're actually in slightly different places this time. And that means that when we do the superposition, there we are. I'm putting the environment in, and these things are all both superposed as well as everything else. Doesn't solve the problem, because you've got superposed environments as well. I mean, usually what people do is they change the rules at this point, and they construct a density matrix. They sum over the different environments, and then they rotate the density. I'm not going to go into all that, but that's one of the conventional arguments. The other thing, people say, oh, well, look, you've forgotten to put in the observer who comes along and looks at the cat. Okay. I don't know if you want it may get a little crowded if I put all those things at once, but here we go. There's the observer looking at the cat, and there is the observer's perception of the dead cat. Now, I don't know how you treat this thing quantum mechanically. Of course, that's the kind of thing we're trying to do, but whether you know how to do that or not, it doesn't make much difference because you can see from the expression on the observer's face that he's perceiving a dead cat and not a live one. And if I did the other one, of course, then we would put the live cat. Here we go, live cat. I don't know, my laser's probably got lost here. Never mind, no, I need the laser. Here we are. Live cat, live environment. Here we go. I think I've got the right one. Doesn't matter too much. I'll leave the environment off. It's just... Oh, here it is. Here it is. Here it is. Put it in. And, of course, now that's the wrong observer. It's the unhappy one. Here's the observer, the happy observer. You see the smile on the observer's face, perceiving a live cat. Does that solve the problem? Well, I don't quite know why, because I just simply put all these things on top of each other. And according to the Schrödinger equation, as Schrödinger himself was pointing out, here we have a superposed expression on the face of the observer and evidently a superposed vision of live and dead cat. Now, if you're following the many worlds interpretation of quantum mechanics, somehow these things are supposed to separate into two worlds. I never quite understood the reasoning behind that, because what the Schrödinger equation is saying, you have a superposed observer with a superposed perception. It doesn't seem to me it solves the problem. Now, I'm going to tell you my answer to the problem. My answer to the problem, you see, I'm going to simplify it a bit, partly because I'm worried about I'm worried about the cat's consciousness. So let's replace it by a lump. Schrödinger's lump now. Doesn't help too much, but it makes it a little bit simpler, and it stops you worrying about the cat, which I think is a good thing. Now here we have superposition of the photon going both ways. If it comes this way, this lump is pushed and moved over here. If it goes that way, the lump is in its original position. Now, I'm going to give you, in a minute, a reason for believing this OR criterion that Stuart and I have been trying to employ in microtubule states and so on. The conclusion is that this superposition of two lump states will spontaneously become one or the other in a certain lifetime that you can calculate. Now, that's not what quantum mechanics tells you. That is what certain reasoning, which I'll run over with you in a little while to try and explain to you, but it's not standard quantum mechanics. Standard quantum mechanics would be, let's suppose the energies of these two things are the same, and each state on its own would be stationary, then the superposition would be completely stationary and would last forever. I'm going to say that there is a time scale for that superposition, which is roughly h bar or h, doesn't make much difference, over a thing Eg. What is Eg? Eg is the gravitational self-energy of the difference between the two mass distributions. So each of these will have some distribution of mass. They may be localized in the nuclei, they may be not very localized, or various possibilities. And you take the difference between one mass distribution and the other, work out what's called the gravitational self-energy of that difference. That's a well-defined Newtonian calculation, and that is Eg. Another way of putting it, if you have simply a rigid displacement of one to the other, as we seem to have here, then it's the energy it would cost you. Just imagine two lumps sitting on top of each other instead of just one lump there, and somehow you pull one away from the other, and you work out how much energy that would cost you purely in gravity. Ignore everything else. And that is the same Eg as we have here. I should mention that this kind of idea was already put forward by Diyoshi some years before I did. He didn't have quite the motivations I did, and I'm going to show you one of these motivations right now. It's a little bit technical, so I'll run through it rather quickly so that I'll confuse everybody, not just the... That's not really the intention. I'm going to try and see, I'm trying to demonstrate why there is a conflict between the fundamental principle of superposition in quantum mechanics and Einstein's principle of equivalence. Now, what is Einstein's principle of equivalence, or Galilei Einstein? Well, here we have Galileo dropping a big rock in a little rock from the top of a leaning tower. He may well not have done it, but it's much nicer to draw his in the picture. And of course, if they're supposed to fall together, and certainly would if there were no air resistance, and you imagine a little bug sitting on one of the rocks looking at the other one, and that bug thinks, at least for this moment when they're falling, that there is no gravitational field. We're quite familiar with these things now with space travel and all that sort of thing, where even though the Earth is sitting right there, the astronaut does not feel gravitational field because that astronaut is falling freely in the gravitational, well, falling in orbit, if you like, not towards the ground, but that's equivalent to this, and the gravitational field is cancelled out. So you can cancel out a gravitational field by falling freely with it, and that is the Galilei-Einstein principle of equivalence. Galileo knew it, Einstein used it as the foundation stone of his general theory of relativity. Now here is the technical part of the argument, which I shall just race through it, but to give you a feeling for it. Why is there an inconsistency with the principle between the principle of superposition and the principle of equivalence? I'm going to imagine here that you're doing an experiment on a tabletop in quantum mechanics, and you want to take into consideration the Earth's gravitational field. Let's just try and do that. There are two ways you could do it. One is the Newtonian way, which would be to pretend that the gravitational field is just like any other kind of field. You do what's called putting a potential term in the Hamiltonian, well-defined procedure, and you work out your wave function and your Schrödinger equation and all that. Okay, that's one way of doing it. The other way is the Einsteinian way, which is you take a freely falling frame, which is the green one. The Newtonian one is is that right? No, the green one is the fixed system. The Einsteinian one is the falling frame. If you take a frame of reference which is falling freely, there's no gravitational field. And you do the whole thing all over again, but without the term in the Hamiltonian, and you transform back, and you find you almost get the same answer. The Einsteinian purple one and the Newtonian green one, what you find is that there's a phase factor connecting them. Well, those of you who know more about quantum mechanics will know phase factors aren't supposed to make any difference. So they give you the same answer. Well, they're experiments. Colella over Werner many years ago did experiments of this nature to show that the principle of equivalence seems to be consistent with quantum mechanics. However, that is true only if you have one fixed gravitational field. Suppose you have a lump. Now, what did you see? Maybe there's a lump here which is superposed in two different positions. Then its gravitational field will be superposed. And if you look carefully at this phase factor, which was supposed to be harmless, you notice that there's a t cubed up here. And if you really know about these things, you will know that that's bad news. It's telling you that these two wave functions belong to different Hilbert spaces. The vacua are different, and you're not allowed to make superpositions. I'm not going into the details here, but I'm not doing anything which is outside conventional physics here. But you do get a contradiction. Because these things are different Hilbert spaces, the vacua are different, you're not allowed to make superpositions. It's one of the rules. What do you do? Well, what you do is you try and make the superposition anyway and try to see what the trouble is. The trouble arises because certain things diverge. You get infinities coming in. And then you say, well, let's try and cut these divergences off or something like that. That's exactly what I'm going to do. Roughly speaking, I'm going to cut it off after a certain time. There's a kind of time scale where this superposition won't going to cause trouble. And that time scale you can calculate from these things here, looking at where the t cubed comes and what its coefficient is, and you can see that the trouble isn't going to hit you until the sort of time scale that I've been talking about. There will be something has to happen after the time h bar over Eg, which I wrote down before. So the argument is that this thing collapses to one or the other, and that saves you. It may be something else goes on. In detail, you'd need a good theory to handle these things, and that theory is not with us. However, you can see that there is a limit on the superposition. It can't last forever, and you can estimate that limit. Now, I'm going to look at this in a space-time way. And Stuart likes doing it this way, so let's do it this way. Here we have time going this way, time going there, not that way. And here we have space, and it's got a kink in it like that. That little kink is the curvature caused by the single lump. Now I'm going to put it into a superposition of two different locations, the green location and the red location. And the red location is pulled off to one side, and so the little bump goes to one side. And it's a superposition now of two space-times. They're a little bit different shape because the lump's in a different place. And then the argument is that this thing can only last for a certain length of time. And this region of uncertainty of space-time geometry, where you have two superposed, is of the general order of what's called Planck scale for geometry. Well, you see, if we work in quantum gravity, these Planck units are the things you do. They're totally unrealistic units for most purposes, but they're very good if you want to do things which involve gravity and quantum mechanics at the same time. The Planck length, the Planck distance, is 10 to the minus 35 meters. That's 20 orders of magnitude smaller than the scale of ordinary particles. The Planck time, 10 to the minus 43 seconds, that's 20 orders of magnitude smaller than the shortest time scales one seems to come across in ordinary particle physics. Ridiculously tiny. And people usually say, well, if you're talking about quantum gravity, these numbers are so ridiculously tiny you can just forget about them. Well, that might be true, except that what about our time scale, h over eg, the decay time of the superposition? You've got something pretty small on the top, which is Planck's constant. You've got something pretty small on the bottom, because that involves gravitational constant. The pulling of the lumps apart from each other is a ridiculously small energy, but you have a ridiculously small number on the top from ordinary scale. So it's a matter of looking at the thing in detail to see whether tau is likely to be a reasonable number. You can't just write it off. The other point I want to make here, and here's where we get back to consciousness, this is the hypothesis that we make, is that every time one of these dies off, you see, something has to make a choice. Is it the green or is it the red? And according to standard quantum mechanics, it's pure chance. The probabilities come from the squared moduli number that I showed you before, but it's pure chance. Now that order of scale, I say, is this Planck scale for geometry order of scale. And the argument here that we're trying to make is that whenever this happens, it may happen in anything. It may happen in the air, in the environment of my original example. It may happen, it's happening all the time. It's the, if you like, it's the way that the quantum world becomes the classical world. See, often people say, well, quantum physics is for small things, and classical physics is, well, you're just making that up of small things, and then somehow you take a limit. That limit doesn't work, because that limit gives you dead cats and live cats simultaneously. It gives you all sorts of things which you don't see. It gives you entanglements with things at great distances which we don't experience. Somehow they all got killed off. Now they get killed off because of this spontaneous measurement, which is what I'm saying. Now this is why I'm not trying to call it consciousness, because if it's all over the place, somehow it doesn't help us very much. I'm calling this proto-consciousness. So this, every time this decision is made, that is an element of proto-consciousness. Maybe you could say the proto-conscious thingamajiggle is deciding which way it goes. It's like a sort of free will it has, if you like. I don't know how you're supposed to look at it, but that is it only becomes consciousness if you have these things coherently organized all together, and then rather than randomness, you begin to see something of a non-computational nature coming out of it. I don't know how that works. That would require some very sophisticated theory in which gravity and quantum mechanics are brought together so that our current theory of gravity, our current theory of quantum mechanics, those two are some kind of limit of some unknown non-computable theory. That's the idea. Now, is this true or not? Well, I've given you arguments to believe it, which are based on, I should emphasize this again, they're based on completely accepted principles of physics. One of them is the principle of superposition of quantum mechanics. The other one is the principle of equivalence in general relativity. Now, they are in a conflict. That's what I'm trying to say. There is a tension between the two. I think many physicists would say, oh, well, goodbye general relativity. However, you might say there's a little bit more case for general relativity to trust that one, because it doesn't have a measurement paradox. quantum mechanics does. You've got to do something about that. Whereas general relativity, okay, you get singularities, that's true, and there are some issues about general relativity, but it's not all the way through. Got this kind of contradiction between the U and the R procedures, which are all the way through quantum mechanics. So my personal view here is to say, okay, we're going to trust the principle of equivalence, at least at that level. And that gives us a reason to believe that your superposition between quantum states have only got a finite lifetime. But is it true with regard to experiments? Well, this is an idealized illustration of an experiment which is still being under construction by Dick Baumeister and his team. Well, some of these people are now not working with it. In fact, I think all of them aren't. But Dirk himself is still working on this, and he has been for over a decade. Let me show you what the experiment is. It doesn't look like this when you see his actual experiment, but the general idea is like this. Here we have a beam splitter. Here, a laser here, sends a photon. This photon is split into two. This one is kept in a cavity. It sort of bounces backwards and forwards and backwards and forwards and backwards and forwards. This one is in another, but a rather curious kind of cavity. It enters this cavity. There is a mirror, which could be hemispherical or something, which focuses the light. It bounces back onto this little tiny cube, which is also a mirror. It's how far big is it? Well, it's about 10 micron cube. It's about 1/10 of the thickness of a human hair. It's just a bit too small to see. With a good magnifying glass, you could see it, I expect. Anyway, and here I have a cartoon of it, and I've indicated all the different nuclei, you see. A photon comes on, bounces backwards and forwards, hits it. It's like a sort of somebody jumping up and down on a diving board. This jumping up and down of the photon gives it sufficient kick so that it moves it just a little bit by about the diameter of an atomic nucleus. And here I've blown up the picture again by showing you the nuclei, and they get sort of displaced with respect to each other. It's a superposition of the red location and the blue location. And the argument would be that if you can get rid of all the problems, the decoherence, you have to good vacuum, the suspension has to be nearly perfect, the mirrors have to be extremely good, able to reflect something like 1,000,000 times without loss, something like that, extremely good mirrors, and isolation from vibration, good vacuum so the odd air molecule doesn't go and wreck it. All sorts of things. A very hard experiment. As I say, he's been working on this for about a year or so, about 10 years or so, about a decade or so. And about 2 years ago, quite uncharacteristically, I said 3 years ago, quite uncharacteristically, he came up to me and said, in 10 years, we'll have an answer. Now, I thought that's pretty good. Usually when people say that, that's a constant of nature. You see them again 10 years later and say, in 10 years, we'll have, that sort of thing. I saw him again 2 years later, and he said, quite spontaneously, in 7 or 8 years, we'll have an answer. Wow. And then I don't think, I'm predicting now that he would say 5 or 6 years if I asked him again, because it's about 3 years ago. Anyway, that's exciting. Maybe we will know. I should say that the 10 years, maybe he'd know earlier, that's assuming that this mirror here is completely uniform. If it's completely uniform, the effect is just a surface effect, very much smaller. If you can take into account the individual nuclei, it may happen a lot earlier. So whether it's going to be 6 or 7 years or even earlier than that, I don't know. I gather from what he said that he saw his way through all the obstacles, one of them being the mirrors, which are very difficult to get to the quality you need. Well, we just have to wait. There are other experiments also looking at this kind of thing. I don't know so much about them. I want to end by just one thing which is more speculative, but it also got some mathematics in it, which I'll only flash at you. I want to give you the idea. You see, the criterion I mentioned up to this point was for a lump in two locations which were basically assumed to be of the same energy as each other. So that was our example here, where these things were at the same height above the table, if you like. Now you might consider a situation where they're slightly different energies. I have difficulty drawing what I mean here, because if either one of these states is supposed to be stationary, and in quantum mechanics, if something is stationary, it has a well-defined energy. If it has well-defined energy, it has, by Planck's formula, a well-defined frequency. And so this has a particular frequency. Now, if they're the same energy, those frequencies cohere precisely. But if they're slightly different, then those frequencies will be a little bit different. And you can expect sort of beats between the two. And I have a sort of mathematical formula to see what it means. You have a quantum frequency, and you get a classical beat between them. Now, that's all conventional quantum mechanics. You can have something where the location are different from the... This is the kind of situation I really mean, and it's hard to draw. That somehow there are two different distinguishable locations of this thing, and the energies are then not well-defined for each location. However, you have well-defined two different energies, which are each well-defined, and then the location is not well-defined. So you have a sort of mixture between the two. Quantum mechanical people know what I'm talking about here, but don't worry too much. You have superposition between the two positions, and that's the sort of different superposition between the two energies. But you get beats between the two energies, and the question is what happens? Well, according to the scheme that I was talking about before, it will find itself in one location or the other location. I don't know where I should be pointing here, I suppose. One location or the other location. But what I'm trying to suggest here, it needs more work to understand exactly how this would come about, but it looks plausible to me, is that under appropriate circumstances, and you get this already in the quantum situation, that the locations have an oscillation to them. That if the energies are well-defined, the locations have an oscillation to them, and so on. Now, if it's in one state of energy or the other, the location will oscillate from one place to the other. So the idea here is that maybe these state will not just reduce to one location or the other, but to an oscillation. And that oscillation will have a phase which it becomes well-defined. Anyway, that's a rough idea. It needs more thinking about. But the point here is that you have two very high frequencies, which are the frequencies for each of these energies here, and you have an oscillation, which is this sort of beat frequency, which is a very much lower frequency if the energies are very close to each other. So that's the idea, and, well, Stuart says I wasn't going to mention microtubules. Here's a picture, a rather bad picture of some microtubules. And the question is, how does this apply to microtubules? It's a very interesting thing to try and develop further. I'm only giving a rough idea. We did refer to this vaguely in our recent review article, but the idea is that OR will reduce it to a classical oscillation. The point is here that maybe it's got something to do with EEG, because consciousness seems to be related to specific frequencies which are measurable. You see, the EEG, you can measure that, so that's a classical thing. Now, is that a reflection of what's going on quantum mechanically in the microtubules? If it's to do with beats, it could be this reduction from a quantum mechanical oscillation with beats in the quantum mechanical sense, and then if that gets up to the scale where the EG, the H bar over EG comes in, then you would get a classical oscillation coming out of it. It needs to be worked further, and I wouldn't make any claims about it at the moment. It does seem to me there is a possible explanation for EEG in this, which I gather from Stuart is a big mystery, and we don't really know where EEG comes from. Maybe it comes from this sort of thing with microtubules. It's something that needs further work, but I thought I'd throw this at you just in case something can come out of it. Thank you very much.
Okay, Dave had a question. Is there another mic, Dan?
I just want to get a bit clearer on how consciousness fits in with the physics, because that part went by fairly fast. So the thought is that once we've got this complete OR theory, it looks like you're going to have a beautiful mathematics of Schrödinger evolution and some orchestrated reduction and so on. We'll have a beautiful abstract mathematical theory, which can be put, like all physical theories, in mathematical terms.
Yeah.
But it looks like it's going to have the same, on the face of it, that mathematical theory will have the same kind of gap to consciousness as all the other mathematical theories we have in physics now. And I take it then the extra move is to label some of that, or to somehow build in proto-consciousness to the very foundations of that theory. I don't know whether you think there's going to be a separate bit of the mathematics that governs sort of proto-consciousness,
Yeah.
and consciousness, which is a wholly separate mathematical component of the theory, or whether we're just going to interpret some of that mathematics as being the mathematics of proto-consciousness. But in any case, I'm just curious, what is the role, the causal role that consciousness will be playing in this theory? The one candidate I heard was that somehow it might play a role in bringing about the reductions and causing the reductions, which I always understood not to be the view that you guys have. But if it's not that, then what?
Yeah, I think there's a bit of a misunderstanding. And when you gave your talk, I meant to mention this.
Yeah.
It seems to me there are two different issues here that are slightly confused. One of them is the idea, maybe von Neumann and Wigner and people had, that I'm not quite sure what Wigner's view was. He may have had more than one view. But that let's say Schrodinger's lump, that the lump remains in a superposition until somebody comes and looks at it. And that lump then enters that person's consciousness, and at that point, it becomes one or the other. And that, I think, is the picture of causation that you're presenting here, that consciousness causes the reduction of the state. Now, I don't like that view at all, for the sort of reason, okay, maybe there's some distant planet, and it's got no consciousness anywhere near, nobody looking at it or anything, and the atmosphere the weather on that planet, we know that weather is a sort of chaotic system, so quantum events are going to influence that weather. That weather is going to be one mess. It doesn't look like anything like a weather. A little satellite comes bzzz up to this thing and takes a photograph, sends the signal back to the Earth, somebody looks at the screen, and boom, it becomes one or the other, or one particular weather. Now, I think that's a totally implausible view of what happens, which is the sort of reason I don't believe that it's the outsider's consciousness which is influencing the superposition to become one or the other. However, in the brain, it's a different story altogether, because there, it's if you like, it's not that one is influencing the other, they're the same thing, is the idea. That the state that makes a choice as to going one way or the other, that choice or that what it's doing is the consciousness going on. So it's not as though even really that one influences the other, they're one and the same. But it's the one here, it's not the one in the piece of apparatus that the observer looks at.
But in the fundamental physics of the brain, I think you need ultimately consciousness or proto-consciousness to be doing something.
Yes.
In the physics. We've
Well,
got
it
this
does.
beautiful autonomous mathematics of the physics.
But it does something here.
And the thing it's
it's
going to
the
be
choice
doing,
of which one it does.
it makes the choice happen.
Yeah,
It is the choice.
it is the choice.
It is the choice.
Yeah.
And why couldn't you have all the mathematics of the choice without consciousness?
Well, look, like any physical theory, you make a theory, a good physical theory, I should say, you make a theory and then you produce its ontology. You say, this thing corresponds to this thing in the world, this thing corresponds to that, this is energy, this is an electron, so on and so forth. Here we're saying this part of the theory, which is the state reduction, is proto-consciousness. That's the theory. It may be wrong, but I don't see why I can't do that with a theory of consciousness in the same way that we do with all other physics. I
Can we
mean,
empirically distinguish it from a theory where there's collapse correlating with consciousness, which is distinct from it?
well, if you like to call it correlate. I mean, what you say with energy, so you've got your physical system and you work out something, you say, oh, this is the energy of the system. Now, of course, it's in some piece of mathematics you're doing, but the mathematics is meant to relate to some thing in the lab, say. And so you say, what is the energy of this? Well, I'm modeling it with this particular mathematical structure, and then I say, this is the energy in that structure, that therefore is the energy of the system. Well, I would do the same thing. I'm saying, I'm trying to model, I'm going way beyond what we can do at the moment, of course. Like I say, I'm trying to model some conscious person's brain, and then I say, in this theory it says, oh, there are these elements of proto-consciousness which are cohering together in an orchestrated way, and therefore, according to my model, that person is having a conscious experience. And then you say, oh, the person said, oh, my God, you're right, I did just have that. Well, I mean, I'm not saying it's going to be as lucky as that, but that's the idea. I don't see why, philosophically, there's a different problem here than there is normally in physics.
Long discussion.
Would you say it's an identity theory? I notice philosophers are always looking for identity theories, but when presented with one, they don't like it.
Well, maybe.
I just don't like them in general.
Yeah.
I wanted to ask a question about randomness in this system.
Yeah.
We all think about randomness as a source of
I'm sorry,
meaningless.
I just missed what you said. We think of
We think of randomness
yes.
as a source of meaninglessness. In other words, it cannot produce meaning. But that seems to me to be an unwarranted presumption. If you could question that, where could that take you? If you could question the idea that randomness and meaninglessness are inevitably one and the same thing.
Well, I think your question relates to something here in this model, because in the normal way we do quantum mechanics, it's supposed to be random. I mean, when you make a measurement according to the R process, you get probabilities out of the squared amplitudes, and that is supposed to be random within those probabilities. And that's the way we do quantum mechanics currently. Now, if you've got this extension of quantum mechanics in which I'm not sure how you treat it. I mean, clearly it's not completely random altogether, because I'm trying to say that understanding is something which is built up from these proto-conscious elements, but not just them themselves. There's memories and all sorts of things as well. But it seems to be that it's not just a random thing at that level, that there is insights, there's understanding, there's something going on which is now brought out, which in the case of the proto-conscious element, it doesn't reveal itself. Now, I think I take a sort of view, since this is all so primitive, I'm not quite sure how to think of it, but I'm taking a sort of view that it's never really quite random. You see these processes. And in some sense, it's the thing choosing which to do.
Well, what I'm questioning is, rather than imputing decision-making power to these entities, which is counterintuitive, instead, could we look at the concept of randomness itself and our identification of it as inherently meaningless? And could we look at it as a possible window through which meaning emerges?
Whether it's got anything to do with the problems people have when they define probabilities. I mean, when you try to be definite and make a rigorous definition of probabilities and that kind of thing, people get themselves tied in all sorts of knots. Because you say, well, you do it 1,000,000 times, it's never quite a probability, because you say that's going to happen with probability. So almost certainly, well, there's always a probability hanging behind it. Right. So there are issues like that. Do they have relevance to this? I don't know, but it's an interesting question.
Thank you.
Roger, I'm growing interested in the experimental searches for the OR phenomena. I'm here in the middle, I guess I'm supposed to stand up.
Yeah.
I'm growing interested in the search for gravitational OR phenomena, and perhaps writing a review paper on the experimental constraints and experimental possibilities for OR. You still don't see me, but that's okay. I have a quick question, something you could shed some light on. State-of-the-art long baseline neutron interferometry experiments where they take a neutron and split it into a high beam and a low beam that may be separated by perhaps 10 centimeters in Earth's gravitational field. Mm-hmm. Now that's a difference in gravitational energy. You may wish to distinguish that between self-energy, but if you don't draw that distinction, you're starting to reach a level where we perhaps should be seeing some sort of precipitated collapse.
No, that's a different situation. It's a question of the gravitational fields themselves being in superposition. For the neutron itself, you would have to be worrying about its gravitational field if this OR was going to come in. As far as the Earth's concerned, and it's got two different energies, it's not two different gravitational fields. They're not being superposed in this situation. I mean, okay, they are, because the neutron has its own gravitational field, but it's tiny. And that will not be significant in this scheme.
Yes, I see the difference.
Okay, right.
I have a question about, you're talking about Schrödinger's cat. That's a macroscopic object. And as far as I know, many physicists have worked on decoherence from the environment, and that actually many believe that the Schrödinger's cat is not really a paradox anymore. So I'm just wondering, you have managed with the whole talk not to talk about the coherence of the environment, which I would say that many physicists would probably ask you, why are you not talking about the coherence of the environment? That might solve a lot of those issues.
It's a part of the story, but it doesn't solve anything. You see, and I don't want to go through this here, but my main trouble with the environmental decoherence point of view, you say you have a system and then the environment gets entangled. You could do it with Schrodinger's cat, but you have a system and the environment gets entangled with it, and then you say, well, it's a question of the ontology. You have to have a consistent ontology. And the trouble with environmental decoherence is there isn't a consistent ontology. You say originally, okay, you might take the view, well, the state represents reality. I don't know if they always do, but let's say that for the moment. Then you say, okay, the environment gets involved in the state. We don't know what the environment is, we don't care, therefore we sum over those degrees of freedom. Now you have a density matrix. Now that density matrix becomes the representation of reality. That's the ontology. Now it's a new ontology. Now you say, we've got this ontology, we can rotate our frame. Stealthily, we rotate the frame round, it doesn't change the density matrix. But we can now adopt a different ontology, which says that you look at the diagonal terms, and you say that these now represent reality. And then you say it with the probabilities that you're given on the diagonal. There's a cheat. It's a double cheat. You see, you first of all, the cheat is only in the ontology. It's not in the mathematics, if you like. You say, okay, what's reality? First of all, it's the state. Secondly, the density matrix. When you're within the density matrix ontology, you can rotate. Then you come back to the state, and you get the thing has collapsed into those states again. But it's not an explanation. However, here, the argument would be that yes, environmental decoherence plays a huge role, but probably that's right, and most of the arguments that people produce with environmental decoherence are okay, because in the environment is most of the mass displacement. I should think, if I have this glass here and glass here, then that will affect all the molecules in the air just slightly. They'll be in slightly different places. They'll bang against each other. They'll be all different. This difference between that set of molecules and this set of molecules will probably give me an EG very rapidly, which will reduce the whole thing all at once. So it will be in the environment. It's the environmental decoherence picture, but with a different, it gives you the role of an ontology which enables you to let the change in the environment collapse the system because it will be an entangled system. That will usually be what happens. So if you have an experimental measuring device, there's the air running around and all sorts of things, and it will normally be the environment which reduces it. But if you take a very, very sophisticated example, like the one that Dirk Bouwmeester is trying to do, you've got to get rid of the environment. That's a crucial thing. You make sure that all the molecules are pretty well removed, there's no vibration, all this sort of thing, and you get rid of all that environment and you have a pure experiment where there's no environmental entanglement in the system. That's the idea, anyway.
Okay, we're going to have to break. Before we thank Roger, I have a brief announcement. You may have seen in the program book the Baumick Prize. Manny Baumick is a physicist at UCLA who invented the excimer laser, which is used in eye surgery. He has a broad range of interests. He's a Renaissance man and a philanthropist. And he donated a $10,000 prize, and he has, with consultation, has designated Roger Penrose as a recipient. So let's congratulate Roger. This is not the actual money because we don't want him getting mugged on the way out. But with that, and I should say that the reason Manny Baumick isn't here is that 5 days ago he required emergency cardiac surgery for coronary bypass. I talked to him this morning. He's about to go home, doing well, and wished us all the best, and especially to you, Roger.
Well, I'm glad he sounds okay. I really feel embarrassed about this because, what do I know about how the brain works and all that? But anyway,
you know what consciousness is. Thank you all very much.
Thank you.